Hi, in this work, we present a style-aware method for animated character representation. We do so using self-supervision by multi-object tracking. This work is a collaboration with Rapoport and Ariel Shamir, myself, Oron. Computer vision state-of-the-art algorithms are applied today on many tasks like detection, segmentation, and others. However, these algorithms work well mostly on photorealistic footage. For example, multi-object tracking is a well-studied field, and ByteTrack is a state-of-the-art multi-object tracker. This amazing work captures all pedestrian in CCTV footage. However, this model works only some of the time on animated human characters, while failing on non-human characters and non-photorealistic styles, like this abstract style where none of the characters were detected. So what makes the difference? For once, animated videos are produced differently. Also, style have high variance. Variance between anthropomorphized characters is high due to shape, style, and animation techniques. We can see here CGI, manga, cutout, and other technologies. Also, characters could wear any shape, which is another challenge. And as physics not always apply in animation, the variance of a single character could be high. For example, this is Cosmo, a fairly simple character with just a few colors and distinctive pattern. Cosmo changes about 30 shapes in a matter of seconds, from fish into jackhammer, toaster, and so on. So we want to take a full-length animated video and generate a style-aware character representation. We segment shots, apply a character detector on sampled frames, run multi-object tracker per shot from those sampled triplets to refine the semantic embeddings of this specific style. The shot segmentation monitors color histogram change to split shots. For detection, we use YOLO V2, which was fine-tuned over our training set of 61 different styles. This detector is applied in the wild, meaning no further training from that point. This model is tuned to be recall-oriented, meaning minimal false negatives. We use SEResNext backbone as our base representation network over the same dataset. For multi-object tracking, we've been using classic max-flow min-cost approach and improved the transition cost estimation function. We leverage the triplet loss idea from FaceNet, which uses 3 images as the unit of analysis for adaptation. 2 examples of the same identity are considered anchor and negative, while an example of a different identity is considered as negative. Mathematically, it compares the distances in the latent semantic space and penalizes if the negative is closer to the anchor than the positive, with some margin. By analyzing a single shot and considering its tracklets, our main hypothesis is that 2 distinct boxes from the same frame have different identity, hence considered anchor and negative examples, while all boxes of the same tracklet have the same identity. Thus, One is sampled and considered as the positive example for the fine-tune. Most of the triplets look like this example, which captures character pose variations. Some cases are non-trivial, like when Cosmo changes shapes. But what happens when the tracker fails, or when the detector has false positives? We believe that although such cases doesn't encode identity properly, it may still adapt the network towards the given style. This image cloud illustrates the first two principal components of the 2048 dimensional representation before and after the self-supervision. One can see that our representation encodes the identity of these three characters much better after self-supervision on the right. Some results. For evaluation purposes, we've collected and labeled an evaluation dataset with 7 series, each having 2 episodes to train and test over 49 characters. The clustering algorithm that worked best for us was dbScan. This non-parametric method doesn't require the true number of clusters, while the character distribution is heavily long-tailed. Also, it disregards noisy candidates, which helps filter false positive detections. Our ablation study shows that self-supervision generates significantly less clusters of more characters, where 90% of the clusters are totally pure, which is better. The first application we present is building dictionary characters. This unsupervised task requires clustering the detected candidates, filtering outliers, and selecting an exemplar per cluster as the character. Here we can see our dictionary derived from the full-feature film Cars 2, which is part of the SAILA MCD test dataset by Somandepalli et al. I love the fact that some different cars with similar color and appearance were clustered separately. One example of error is the oversegmentation of the red car Lightning McQueen, as it is the star of the movie with the highest frequency. The following characters were captured from the South Park video on our cast evaluation dataset. The highlighted characters are long-tail characters. No repetition were found here. One failed case is this non-character example of a tree. Somandepalli et al. Have suggested the dictionary building task. Our method have outperformed the results on their test dataset with respect to all metrics, introducing much higher cluster purity and much less exemplars per character. The second application uses the previous steps and the human in the loop to label clusters. Using this method, we can build character classifiers with minimal effort. The following statistics were evaluated over our evaluation dataset. The pipeline was applied on each training episode and tested over the test episode per series. This approach has yielded about 89% F1 score by only labeling clusters. The third and last application further applies this method on all frames, yielding full labeling. Here we apply the image classifier trained based on our method on its test episode. frame by frame without temporal coherency, which is left for future work. This approach empowers media companies to estimate the screen time per character. This opens the door for gender bias estimation in animation, for instance. We've found, for example, that the movie Cars 2 gives only 20% of the screen time for female characters. To summarize our work, I presented our method for representation learning of animated characters using self-supervision by multi-object tracking. 3 different applications were suggested to showcase its power: movie dictionary building, training set labeling, and full labeling and statistics extraction. Thank you.